Great. So let's move on to the next talk. The next speaker is Satvik Singh, who is going to tell us about the distillability of entanglement. So please.
All right. Thank you for the introduction. I'm going to talk about some good old entanglement theory today. This is joint work with my PhD supervisor, Nilanjana, at Cambridge. All right, so this is the archive identifier for those of you who are interested in more details. All right, so let me jump right into it. So usually entanglement distillation is studied in a bipartite setting. And the basic task in this distillation procedure is that there are two parties, Alice and Bob, and they initially share, let's say, n copies of some mixed bipartite state, let's say rho AB. And their aim is to obtain some mn copies of the Bell state, of the 2-qubit maximally entangled state, by using only local operations and maybe some classical communication. Now, the one thing to note here is that the classical communication configuration between the two parties matters in this procedure. So if we allow communication only in one direction from Alice to Bob, then this is a different task. And then maybe if you allow backward communication from Bob to Alice as well, then maybe you might be able to do better because you're adding another resource. So if you just have one-way communication, then we say that the procedure is one-way LOCC, or if we have back and forth communication between the two parties, then we call the procedure two-way LOCC, or two-way local operations assisted with classical communication. Now, if in the asymptotic limit of the initial number of copies of the state going to infinity, if the distance between the extracted mn copies of the Bell state goes to 0, then the rate at which these Bell pairs are being generated in the asymptotic limit is called an achievable rate for distilling entanglement from your original state. And it would be either called one-way achievable rate or two-way achievable rate, depending on what kind of classical communication configuration you allow between the parties. And then finally, what you just optimize over all possible one-way LOCC or two-way LOCC operations to arrive at the quantity of interest, which is the one-way or two-way distillable entanglement of the state. Now, clearly, two-way distillable entanglement is going to be at least as large as one-way distillable entanglement, because as I said, if you're allowing backward communication as well, then you're allowing the parties to more resources essentially. And so this just essentially follows by definition. All right, let us also recall that a bipartite state is called separable if it lies in the convex hull of product states. So basically you can write it as a convex mixture of product states. It is called PPT if it remains positive under the operation of partial transposition. So you just apply transpose on one part and your state stays positive under that. If it stays positive under this operation, then it's called PPT. We call the state two-way undistillable if the two-way distillable entanglement of the state is 0. And similarly, we can define one-way undistillability. Now, clearly, I mean, all these forward implications from 1 to 2 to 3 to 4 are well known. In particular, it is also known that this 1 to 2 implication is strict, or in other words, there are PPT states which are not separable. And the implication from 3 to 4 is also known to be strict, meaning that there are states which are one-way distillable, but they may not be two-way undistillable. However, we do not know if the 2 to 3 implication is strict or not, and this constitutes the famous NPT-bound entanglement problem. So we do not know if the PPT property of a state is equivalent to its two-way undistillability. In other words, we do not know whether every NPT state or every non-PPT state is distillable or not. And this relates to the problem that we're going to see next. All right, so now what we're going to do is we're going to bring in a third party, let's say Eve, so that the three parties, Alice, Bob, and Eve together share a purification of the original bipartite state rho AB. And then in this setting, Alice would then share the complementary state, which is just defined as, instead of tracing over the environment or Eve, you now just trace over Bob, and then you get a separate, a different reduction, rho AE, which is called the complementary state of the original state AB now. And in the usual distillation setting, if Alice and Bob are performing the distillation procedure, then as maximal entanglement is established between Alice and Bob, Eve gets more and more uncorrelated from both the parties, right? This follows just from the monogamy of pure maximal entanglement. But now imagine that Eve is not really our adversary, but is actually our friend. Eve is now our friend, so that Alice can also classically communicate with Eve, so that Alice can either choose the reduction with Bob, that is rho AB, or the reduction with Eve, that is rho AE, in the distillation scheme. And depending on which of these two states gives her the best rate of distilling entanglement, she can choose either one of these. And so we obtain these 4 max distillation quantities, depending on what classical communication configuration we allow between the 3 parties. So for instance, if we allow two-way communication between both Alice and Bob and Alice and Eve, then we obtain this first quantity here, which is just the maximum of the two-way distillable entanglement of rho AE and rho AB. And similarly, depending on the other 3 communication configuration, you can define the other 3 relevant max distillation rates. And similarly, we can define fully undistillable, the notion of full undistillability, which basically just means that we say that this tripartite pure state is two-way fully undistillable if the first quantity here is 0. And two-way basically means that you allow two-way communication between both Alice and Bob and Alice and Eve. And similarly, you can define 1, 2, 2, 1, and just simple one-way full undistillability by making the other 3 quantities 0. All right, so this is like the basic setting. And now let me briefly describe what our main result says. So basically what we kind of resolve a tripartite variant of the NPT bound entanglement problem. More precisely, we have a tripartite pure state psi that is shared between Alice, Bob, and Eve. And what we claim is that the following statements are equivalent. So the first statement says that both rho AB and rho AE, the 2 reductions, are separable. This is equivalent to the 2 reductions being PPT, which is further equivalent to the tripartite state being two-way fully undistillable. So in this tripartite setting, two-way full undistillability is indeed equivalent to the PPT property of the 2 reductions. And it is in this sense that the NPT bound entanglement, the tripartite version of this problem is solved. And this is not, and even further, we can actually say something more. These 3 statements are further equivalent to the state being 2, 1 way fully undistillable, and also 1, 2 way fully undistillable. Now, clearly, if the state is 2 way fully undistillable, meaning 3 holes, then 3 implies 4 as well, because you're just cutting off a backwards communication line from Bob to Alice, right? But 4 implies the implication, the reverse implication is the non-trivial one, because it is certainly reasonable to imagine that this quantity is 0, but allowing backwards communication from Bob to Alice, makes the quantity on the 3rd statement non-zero. So the reverse implication is the non-trivial one. And just so that we are on the same page, let me describe the same thing again now with this figure in mind. So let me recall that we have 3 parties. They share a tripartite pure state psi, and the task is for Alice to distill entanglement either with Bob or with Eve, depending on which state gives her the best rate. And our result basically says that if any one of these 3 communication configurations is useless for the stated task, then so are the other 2. And this happens precisely when the tripartite pure state is such that both the reductions rho AB and rho AE are separable, which is further equivalent to the reductions being PPT. All right, so let me quickly state a very simple corollary of this result, which can be considered a partial resolution of the usual NPT bound entanglement problem of the bipartite case. So basically, the corollary says that if you have a bipartite state which is not PPT, then either you can distill entanglement from the state itself, or you can do it from its complement, and this is in the two-way setting. And why is this true? Well, I mean, if you assume on the contrary that you cannot distill entanglement from both rho AE and rho AE via two-way LOCC, then from the previous, our main result, we just saw that this was equivalent to both the reductions being PPT at the same time, which just immediately leads to a contradiction because we assume that rho AB was NPT to begin with. So this shows that if you have an NPT state, then even if you cannot distill entanglement from the state itself, you can do it from its complement. And so this kind of resolves a kind of like a partial resolution of the original bipartite formulation of the NPT bound entanglement problem. All right, so let me now quickly go to some ideas for how this result can be proved. So basically what we exploit some entanglement or distillability properties of low rank quantum states. Before stating what exactly I mean by low rank state, let me recall the hashing bound, which basically says that for any bipartite state rho AB, the coherent information of the state is an achievable rate for one-way distillable entanglement. And the coherent information here is just the entropy of the reduced state on B minus the entropy of the actual state itself. So if your rho AB is such that its reduction on the B subsystem is maximally mixed, then this hashing bound immediately tells us that the one-way distillable entanglement is going to be at least as large as log times RB, because the entropy of the reduced state now is just the maximum possible. And the entropy of the original state is upper bounded by the log of the rank of the state. So you immediately obtain this bound. And so you obtain a bound on the two-way distillable entanglement. And if you assume that the rank of your state is strictly smaller than the reduced rank, and this is the low rank assumption, then this quantity becomes non-zero. And so every low rank state which satisfies this condition is two-way distillable. But we want to get rid of this condition here because we don't want to assume initially that your reduction on B system is maximally mixed. So what we have is we have this theorem. So for any quantum state or for any bipartite state rho AB, which is of low rank, meaning that the rank of the state is strictly less than the rank of the reduction on the B subsystem, we have this bound on the two-way distillable entanglement. Instead of having this rate, we now have this rate multiplied by some factor. But the point to note here is that this is still strictly bigger than zero. And so every low rank bipartite state is actually two-way distillable, and we actually have a lower bound on this quantity. And the way to prove it is that we basically apply a local filtering procedure. So Bob selects this kind of a generalized measurement corresponding to two outcomes, and one of the outcomes correspond to this measurement operator, and which is basically defined as follows. You take the reduction on B and you take the inverse of the square root of that. And this is understood to be taken on the support because this operator may not always be invertible. And so after Bob applies this filtering procedure, you get this filtered state rho prime, which is just given by this expression. And why are we doing this? Because now for the filter state, the reduction on B subsystem becomes maximally mixed. So you can now apply the hashing bound, and which gives you the rate. But now we want to take into account this probability with which this operation succeeds, and this gives us the factor in front of this rate. A crucial point to note here is that two-way communication is essential in this proof, because after applying this filtering operation, Bob would want to communicate back to Alice to say that the operation succeeded. Because if it did not succeed, then they would have to kind of discard the states for which this operation failed. And so two-way communication is essential here. And this is why the proof fails if you just allow one-way communication from Alice to Bob. In fact, what you can show that even though all low rank states are two-way distillable, which we just proved, they may not always be one-way distillable. And you can construct concrete examples of low rank states which are two-way distillable, but not one-way distillable. However, if on top of the low rank assumption, you assume something more, which is an additional rank constraint given as follows. So what you do is you assume, first of all, the low rank assumption, the low rank constraint, you assume the low rank constraint, and then you assume that there exists a pure state on Alice's subsystem such that the rank of this object is this. Now, let me clarify what do I mean by this object. So this rho phi sub B is basically like a partial trace over A, but with respect to this pure state on Alice's subsystem that we have assumed to exist. So you can show it very easily that this object has always rank, which is upper bounded by the minimum of the rank of the original state and the rank of the reduced state on the B subsystem. So this bound always holds for any pure state analysis subsystem. But what we are assuming additionally in this theorem is that this bound actually gets saturated for some pure state phi A. So just to summarize, if you have a low rank quantum state which additionally satisfies this rank constraint, then you can actually distill entanglement by just using one-way LOCC. And the proof here is quite similar. Instead of now Bob applying the filtering operation, it is Alice who applies the filtering operation, which is defined in exactly the same way as before. But now, since it is Alice who is performing the filtering, she can communicate the results of the operation to Bob, because Alice to Bob communication is still allowed, and they can discard the states for which the filtering failed and proceed with the rest of the protocol. But now the crucial point here is that now, instead of the reduction on B being maximally mixed, it would be the reduction on A that is maximally mixed, and which basically means that this filtered state rho prime can now be considered as a valid choice state of some quantum channel phi from A to B. And now our idea is basically to show that this channel has positive capacity to transmit information, and then relate the distillable entanglement of the choice state to the capacity of the channel to send information to obtain the desired result. In other words, we want to show that this channel has strictly positive coherent information, and this combined with this bound, which basically says that the distillable entanglement of the choice state of any channel is at least as large as some dimensional dependent factor multiplied by the coherent information of the channel. And this holds for any channel phi. So if we assume these two things, then it's clear that since the LHS is positive, the RHS is also positive, which is exactly what we want to show. We want to prove positivity of the distillable entanglement of the state that we started with. So we want to prove these two things. So let me first tackle the bound. I mean, I'm not really going to tackle it. This requires a certain teleportation argument. And for those of you who are interested, you can look up the paper. So I'm just going to assume that this bound holds. And now, in order to show positivity of the coherent information, let me first actually recall, for the benefit of the listeners, what exactly is this quantity. So this coherent information for any channel is defined as follows. So you basically, Alice takes a pure input state, a bipartite input, where A prime is some reference system, and the A subsystem is sent through the channel phi, and then you compute the coherent information of the resulting state, and then you optimize over all possible inputs, and this gives you the coherent information of the channel, and the regularization of this quantity gives you the full quantum capacity of the channel. And we want to prove that this quantity is positive, and we do this by applying some recently obtained results. So basically, results by Vikesh Sidhu and by me and Nilanjana from last year, they can be used to show that if phi from A to B is a channel such that its Choi state, the rank of the Choi state is strictly smaller than the rank of the reduction of the Choi state on the B subsystem. If this is the case, and on top of it, if there exists a pure state input phi such that the rank of the channel acting on the state is this minimum of the two ranks, then your coherent information of the channel is positive. Now, these two conditions seem pretty familiar, because these are exactly analogous to the conditions that we originally assumed for our state. And so these conditions that we assumed on our state translate to the assumptions that are required to show that this channel phi has positive coherent information. And so this is kind of the main technical result of our paper. This allows us to use the techniques that were recently developed to show positivity of quantum capacity of the channel to actually study distillability of quantum states via this bound, which is also like a slightly non-trivial result. All right. So now, if we have this theorem, what we can now establish is this result, which basically says that if you have a bipartite state rho AB such that its complementary state rho AE is one-way undistillable, then the following quantities, the following statements are equivalent. Basically, the separability of the original state becomes equivalent to the PPT property of the state, which is further equivalent to its two-way undistillability. And the way to prove it is, first of all, observe that 1 implies 2 and 2 implies 3. The forward implications are trivial to prove. So we just need to prove that 3 implies 1. And what we just proceed, we just straight away apply the previous result. So if we assume that the 3 is true, then since rho AE is one-way undistillable, it must be the case that rho AE satisfies this rank assumption, right? It cannot be low rank, because then our previous result would show that it is actually one-way distillable. So since we assume that rho AE is one-way undistillable, we must have either that rho AE is not low rank, or it might be the case that rho AE is such that for all inputs in pure input states on Alice's side, the second rank constraint that we assume gets violated. So the previous theorem requires these two conditions together, and if we negate this, we get an OR negation. Either this is not true, or the second constraint is not true, which is precisely what we are showing here. And then the point is that once you have these two conditions, we can already exploit some previously known results on entanglement properties of low rank states to deduce our result. So if the latter condition is true, then you can use the result by Chen and Dokovic, I believe, from 2011 to actually prove that the rho AB is two-way distillable, which contradicts our assumption. If the former condition is true, then you can apply some previous results by Hrodecky and Vidal, Chirac, by its early results from 2000s, and relatively more recent result by Chen and Dokovic, I believe, again, to show that your state is separable. So the crucial part was this first reduction, in which we employed our previous theorem, this one, and then you can use previously known results to obtain the desired statements. At this point, I think I should mention that a similar result was earlier obtained by Hayashi and Chen in 2011, which obtains the same equivalences that I just explained before, but they assume that the complementary state is PPT, which is like a much stronger constraint than just one-way undistillability. So PPT property in particular implies two-way undistillability, which further implies one-way undistillability. And from two-way going to one-way, this implication is strict. So this can, in other words, this result can be considered as a generalization in some sense of this earlier result that was obtained with a much stronger assumption on the complementary state. And then using very similar techniques, you can actually prove that if now, instead of just one-way undistillability of the complementary state, if you now assume two-way undistillability of the complementary state, then in fact, separability, PPT property, two-way undistillability, and one-way undistillability of the original state rho AB all become equivalent. And I'm not going to go into the proof of this, but the idea is very similar to what we just saw earlier. And now if we assume that we have these two theorems, then what the proof of our main theorem becomes almost trivial. So let me recall what our main theorem was. Our main results basically said that if you have a tripartite pure state psi ABE, then these 5 statements are equivalent. Now, note again that forward implications are again trivial to obtain. 1 implies 2, 2 implies 3, 3 also implies 4. And so let's just see how we can obtain the first statement from the fourth one. So if we assume 4, then what we are basically assuming is that the row AB state is one-way undistillable. And we just saw that if this is the case, then two-way undistillability of the complement is equivalent to its separability, right? And similarly, 4 also says that row AE is two-way undistillable. And if this is the case, we saw from our previous result that one-way undistillability is equivalent to separability. So we obtain our desired result. I guess that's about it. That's all what I had for this talk. These were some of the references that I used. Thank you for your attention, and I would be happy to answer any questions that you might have.
Thanks, Satvik, for an interesting talk. So is there any question? You can also type your questions into the chat as well, or mute yourself to just speak up.
Okay, I have a question. Yesterday, Felix said that the by PPT conjecture is proved for quantum channel. So I'm wondering whether the theorem, I mean the first and the second one, can be used to prove the
exactly.
I mean, by the conjecture.
Yeah. So all of the theorem in the language of quantum channel basically says that if the channel and its complement are both PPT, then they both must be entanglement breaking at the same time.
Yes.
So the first and second statements is actually the resolution of the bi-PPT problem that was raised by Felix and Christoph in their paper.
We know that it is not easy to prove that, but here it seems that the proof is, I mean, not so.
Yeah, I mean, the bi-PPT paper was actually also, I mean, I was one of the co-authors of that paper as well, and that was kind of the bi-PPT argument kind of motivated me to kind of generalize this result further. So the bi-PPT conjecture, the resolution of the bi-PPT conjecture is just equivalence of these first 2 statements here. But now this theorem is kind of extends that result even further to include the equivalences with two-way full undistillability and these other full undistillability statements.
Okay, thanks.
Thank you for the question.
Is there any other question?
Well, I mean, if there are no questions, let me just say that the actual NPT bound entanglement problem is still open. I think I forgot to add an open problem side. So, I mean, yeah, so this is like kind of like a partial resolution of the NPT bound entanglement problem, but it's only partial and the actual problem is still open. And the problem is to tell whether every NPT state is two-way distillable or not.
Okay, thanks. So with that, let's thank Satvik again for a nice talk.